All right. Today we shall begin with the discussion of power transistors. Okay. In short, they are also called as thyristors. So they are PN devices. So far we have studied PN layered devices. We have studied about PNP transistors and also NPN transistors. Okay. Now what if there are 4 layers? Okay. For example, PNPN, or it could be NPNP. Okay. So such type of devices also play a crucial role in E&C. Okay. Especially with respect to the power electronics field, they find a wide variety of applications. Okay. So alright, so let us just begin with the discussion of PNPN devices, which are also called as thyristors. So the wide range of 4 layered PNPN devices are, to start with, SCR. SCR is also called as silicon controlled rectifier. Okay, we know what a rectifier means. Well, a rectifier is a device which converts AC to DC, right? Okay, but we haven't so far studied about a controlled rectifier. Okay, so there will be a special terminal which actually controls the rectification action with respect to anode and the cathode. Okay, so we'll try to understand the working principle about a SCR in detail in this class. Okay, so that's a very important topic with respect to your curriculum wise. Then the second one is silicon controlled switch. The third one is gate turn off switch, which is called as GTO. The fourth one is LASCR, which is also termed as light activated SCR. So it's a slightly specialized form of SCR. Then finally UJT, which is again a very popular device. Its full form is unijunction transistor. Okay, so in your syllabus we have stressed upon SCR, and there are 2 variants of SCR called as diac as well as triac. So all these 3 devices will be studying in detail, followed by the working principle of UJT. Okay, others we will only be what you can say, highlighting. Okay, just briefing upon. Others we will be studying them in detail. Okay. Alright, so begin with SCR. SCR stands for silicon controlled rectifier. Some important points about SCR. It was first introduced in the year 1956, so it's a relatively very old device by Bell Telephone Laboratories. SCR is a rectifier which is constructed out of silicon material with a third terminal for the controlling purposes. So we'll have to focus on this controlling terminal, right? Okay. Silicon was chosen because of its high temperature and power capabilities. Even today most of the thyristors are silicon based, and most of the SCRs are silicon based. Now where do we use them? Where do the SCRs find their applications? Well, the common areas where the SCRs are used are in relay controls, time delay circuits, regulated power supplies, static switches, motor controls, choppers, inverters, battery chargers, protective circuits, heater controls, phase controls. Well, all these come under, somewhere we can just state that they are being used in some electrical applications, or to be specific, some electrical appliances itself. Okay, fine. In the recent years, SCRs have been designed to control powers as high as 10 megawatts. So just focus on this high power capability of an SCR. So because of which an SCR is also called as a high power device. Okay, see, we cannot use our CMOS devices for high power circuits. Okay, all these MOSFETs and all, they can be used to a certain extent, mid-range powers, especially we normally use them in low power applications. whereas these SCRs and all, they can be used for some extremely high power applications, with an individual ratings of 2000 amperes, very huge, at 1800 volts. Okay, so these are definitely high power devices. They are used in high frequency applications such as induction heating and ultrasonic heating. So in induction coils and all, in the microwave ovens and all, we will be using these SCRs. Okay, all right. So now just to look at the symbol of an SCR, how does it appear like? Well, that's the symbol of a SCR. Okay, so there are three terminals. The first two terminals are the same anode and cathode, okay, which we have in the case of a normal diode itself. The third terminal, which is special here, which is not present in our normal diode, is the gate terminal. Please don't confuse this with the gate terminal of a MOSFET. Okay, there the gate used to act as voltage controlled terminal. Okay, but here the purpose of the gate is somewhat different. Okay, we'll be trying to understand these things. So what is the function of the gate? Well, gate determines whether the rectifier switches from open circuit to short circuit. In the sense, it controls its switching action on to off and also off to on, vice versa. Okay, so that's the purpose of using a gate terminal in this case. Okay, so in short we can say that the gate acts as control terminal, and overall an SCR is a controlled rectifier. Well, to be specific, it is gate controlled rectifier. Okay, and here the current flows through the gate terminal. Okay, in the case of JFETs, MOSFETs, the current was 0, right? Ig was 0 there. Okay, because of which it actually acted as a voltage controlled device. But here gate current literally flows. Okay, so it's not a voltage controlled device. Please bear it in your mind. Then coming to its simple or the basic construction. Well, it is a 4-layered structure, and the 4 layers are P, N, P, N. Okay, so broadly I can say that it's a combination of 2 transistors. So here I have one PNP transistor which is interconnected with a 3-terminal NPN transistor, right? So if I want to draw its equivalent circuit, then there will be 2 transistors involved in the case of SCR. Okay, in the coming slides we will be looking at the circuit also. Fine. Okay, then these are the commercially available silicon controlled rectifiers. Okay, some of them, although they appear in some different shapes and structures, but their purpose is the same. Okay, they act as power devices. So how do you identify the terminals? Okay, well, just hold the notch and then you can just identify the terminals. So that's the anode, gate and the cathode. Okay, well, now let us try to understand its working and as well as the characteristics of a basic SCR. I request the students to please be very attentive. Okay, alright, so let me just draw its basic structure and then try to understand its working with respect to its basic structure. So basic structure of SCR. Well, it's a 4-layered structure, so I'll be drawing all the 4 layers first of all. So that's the first one, second one and the third and as well as the 4th layer. So this is P, N, P, N. So now we have got all the 4 layers. What about the junctions? Since there are 4 layers, then obviously there will be three junctions. So let me call this as junction 1, and let this be junction 2, and let this be junction 3. Okay, let this be junction 3. Okay, now let me just apply a bias to it, okay, a forward voltage, which means P region must be connected to the positive terminal of the battery and N region should be connected to the negative terminal of the battery. Okay, so let me call this as VF. VF means the forward voltage, and simultaneously let me also draw the graph so that I can parallelly represent its characteristics. Okay, so let this be forward voltage VF, and whatever current flows, let me indicate it as IF. Okay, so IF stands for the forward current which is flowing through a SCR. Okay, fine. So now as VF increases, right, what may happen? See, we are applying a positive potential to the P region and negative potential to the N region. However, we still have two regions wherein one is of N type and the second one is of P type. So we'll have to understand the working of this basic structure junction wise. Okay, so there are three junctions. So let us try to understand what will be the status of every junction now. Okay, so students, can you tell me what will be the status of junction 1? Will it be forward biased or reverse biased? Okay, so P region is connected to the positive terminal and in turn N region is connected to the negative terminal. So obviously this should be forward bias. FB stands for forward biased. Similarly, what about the junction J2? Well, I am applying positive terminal to the N. Okay, please note that when I am considering junction J2 or N and P region, you will have to ignore the first region or the first layer. Okay, because it is a relative potential between two layers. So now due to the applied polarity, I can say that junction J2 is reverse biased. Hope you can understand, students. Now what about the third one? Well, positive voltage is being applied to P and negative voltage is being applied to N. So that means junction J3 is forward biased. Okay, now what should be our prime objective? Our prime objective is to ensure that current flows like this, right? However, for that all the three junctions must be forward biased. Now, is it so? No, only two junctions are forward biased, whereas the second one, the central junction, is reverse biased. So reverse biased in the sense the depletion layer will be slightly enlarged here, slightly enlarged. Okay, this actually blocks the flow of majority carriers from one region to the other region. However, there will be flow of minority carriers. Okay, see, now the point is, for the flow of majority carriers, this junction J2 is blocking it. Okay, so whatever current flows will be due to the minority carriers. So as VF increases more and more, I repeat, if I further go on increasing VF, this junction J2 will get more and more reverse biased, right? It gets more and more reverse biased. So due to which only the minority carriers may flow, resulting in a small amount of current. Okay, so this stage, this region, right, let me call it by a name which is given as forward blocking region. Forward blocking region, I'll just indicate it. Okay, so from here till here it is called as forward blocking region. So will there be any current in the forward blocking region? No, there will not be any although there may be a very small amount of current which is primarily due to the minority carriers, but majority carrier current will not be there. Okay, fine. Now let Vf further increase. Okay, if it just goes on increasing, what happens to the depletion region here? Okay, see, let's not worry about junction J1, the depletion width of J1 and J3. Why? Because those two junctions are forward biased, so the majority carriers will be flowing. What is important for us is only the depletion region width of junction J2. So as Vf further increases, the depletion region width increases, goes on just increasing. Okay, this in turn creates a problem. Okay, what will happen in a normal reverse biased junction if the reverse voltage just goes on increasing? At some point of time, okay, there is a sudden surge in the current which is called as breakdown current, right? So the same thing happens here also after a certain stage. Okay, so let me just denote it. After a certain voltage which is called as VBR, okay, due to continuous increase in the depletion region width, the potential between the junctions reduces. I repeat. Okay, see, please understand, Vf is the forward voltage which is being applied by the external source, right? However, the voltage, okay, with respect to, or the reverse potential which gets developed at the junction J2 also adds to the forward voltage, due to which the overall or the collective voltage suddenly decreases. Okay, and after that point there is a sudden surge in the current almost linearly. Okay, this is something strange, but this is completely physical, right? Okay, so let me just write VBR is called as breakover voltage. Okay, so what is the significance of that? It is beyond the breakover voltage that there will be avalanche breakdown at junction J2, okay, due to which extremely high amount of carriers will get generated and they will result. Okay, see, please understand, if more number of electrons do get generated, then they'll just move in this way. If more number of holes get generated, then they'll just move in this way. Okay, so electrons will be moving from negative to positive terminal, and holes will be moving from the positive to the negative terminal, thereby contributing to this current, linear current, which is called as forward conduction current. Forward conduction current. Okay, so this is what happens, right? Now the problem is, when can we observe such a forward conduction current? At what particular voltage? Is it just at 5 volts, 10 volts, 15 volts? No. Okay, it occurs at an extremely high voltage. It could be 500 volts as such. Okay, for example. Why? Because the breakdown has to happen, right, at junction J2. Okay, so is there any way to reduce this this point? Yes. Okay, there is a way to reduce it, and the way which is being employed to reduce it is by using a third terminal called a gate. Okay, so now we'll try to add that third terminal. Okay, so just observe, where do I add it? I'll be adding it here, right? So, and the applied potential is also like this. Okay, please observe. Okay, so what is the status of junction J2 now? sorry, what is the status of the last thing, okay, the last one. Okay, just observe. We are trying to apply a forward voltage, right, okay, to the P region, and a negative voltage to the N region, which is the junction J3. See, please understand that VF is trying to reverse bias the junction J2, VF, okay. However, due to the additional terminal which is being applied, let me just call it as VG, okay, the voltage applied at the gate, due to which a current IG flows, okay. Please understand, VBR, okay, at this point of stage there was no gate current, IG was 0, okay. However, the problem was that we need a very high voltage, a very high forward voltage, almost 500 to 600 volts, okay, because it is only after that we are going to get the forward conduction current, okay. Now if I want a relatively lesser forward current, okay, then I'll have to apply this gate, okay, gate voltage, due to which a gate current will be flowing, right, okay. So when that happens, just observe, okay, something interesting happens here. A current IG will be flowing, okay. See, we are applying positive potential to the P region, however VF is trying to reverse bias it, okay. So on a whole, what happens is that electrons, okay, which are here, due to the applied polarity, okay, they have to move in this direction due to the applied polarity, right, okay, because they are supposed to complete a path. However, the reverse bias here, it is so huge that some of the electrons will just enter into this region without completing the path, okay. So when that happens, the depletion wall will just vanish, okay. Please focus on this particular thing, okay. This just goes off, due to which the electrons will just flow in this path, okay. So the point is, let me just call it as IG, okay, and when we apply it, let it become IG1. So for IG1, how do the characteristics look like, okay, they appear like this, okay. So this is the point IG1 flows, okay, and it is greater than IG, okay. IG in the sense, IG is 0 current stage, okay, whereas IG1 is the real current which actually flows whenever we are applying the third gate terminal, okay. Similarly, if I further increase the strength of VG, then I'll have this somewhere here, okay. So this point is called as IG2. If I further increase, I may get a characteristic almost like this, almost a linear one, okay. So let me call this as IG3, okay. Now the point here is, as I just go on increasing the voltage at the gate, more and more gate current flows, due to which I can obtain forward conduction current at a comparatively, at a relatively lesser forward external voltage VF, okay. You will have to understand this, it's a slightly complicated process, but it has to be well understood, fine. Now what is the significance of this particular point then, okay, this particular point, right. So let us call it as this is called as IL. Okay, where IL stands for latching current. Latching current. So it is okay. So it is the current which starts flowing through a silicon controlled rectifier. Okay, so after IL itself, the real forward conduction current flows. Okay, or in short, if I say that IA is the anode current which is flowing, let me just give you an example. If IA is the anode current, okay, what do you mean by anode current? Let me just draw the symbol. Okay, if this is the gate terminal VG, and if this is the anode and then the cathode. Okay, so the current which will be flowing will be IG, right? So that's the controlling current, whereas the real current, the rectification has to happen in this way, right? Okay, the real current will be flowing from the anode to the cathode. Okay, fine. So if I consider that to be IA, then I can say that if IA is greater than the latching current IL, then SCR will be turned on. Okay, please understand this significance. Okay, fine. Now what if I want to switch off the SCR? Okay, what if I want to switch off the SCR? Okay, see, if I just remove this VG, is it sufficient? Okay, suppose if I just detach VG, then will this forward characteristics follow the same path as it is? No, it's not going to follow it. Why? Because even though I remove VG, okay, just due to this forward voltage, there will be a continuous flow of charges through the device. Now the point is, once the SCR gets fired, okay, fired in the sense once it switches on, even if you remove the controlling voltage, even if you make IG equal to 0, you cannot switch off the SCR. Okay, the current will just flow, right? Then how do we switch off it? Okay, how do we switch it off? So there are two methods for switching off the SCR. I'll just be writing them. Switching and switching off. Switching off an SCR can be done by two methods. The first one is called as anode interruption. Okay, what do you mean by anode current interruption? Okay, so what do you mean by anode current interruption? Just remove the input voltage itself. That is one way. And the second way is apply a reverse voltage or a reverse pulse at the gate, okay, which is called as forced commutation. Okay, we will not be focusing much upon these things, but just remember that these two are the methods to forcibly switch off an SCR. Okay, you cannot naturally switch off an SCR. Okay, see, because normally what happens in the case of MOSFET, okay, there gate was acting as a controlling terminal, right? If I apply a bias to the gate, then the device would have turned off. If I remove the bias, if I remove the gate voltage, then the device would have turned off. Okay, however, that doesn't happen here. Okay, all right. Now when anode current interruption or forced commutation is being done, then the forward current it doesn't follow the same path. It will slowly come down like this, okay, and then follow the path, okay. However, there is one more point to be understood here. The point is, this particular, if I just extend it, okay, if I just extend the linear curve, then I'll be getting a point which is called as IH, okay. Well, IH is called as holding current. Holding current, okay. So what is the significance of it? If the anode current is made lesser than the holding current, only then I can switch off the SCR, okay. So that means the latching current IL and the holding current IH, they have more significance, or these two current stages are extremely important with respect to switching on and switching off of a particular silicon controlled rectifier, okay. So this was all about the forward characteristics. What will happen if the gate voltage is reversed? What will happen if the input voltage, which is VF, is being changed from forward bias to reverse bias, okay. See, so far we were discussing only with respect to VF, right? That is in the first quadrant. Now let us try to discuss about VR. Okay, let me just select a different colored pen so that, okay, fine. Now if I apply a reverse voltage VR, okay, reverse voltage in the sense, this should be made positive and this should be made negative. So this is negative, positive, okay. That means I am applying negative voltage to the P side and positive voltage to the N side, right? So in this case, what will be the status of these three junctions? Okay, now again I will have to understand it, okay. So I'll be writing it here. So during the reverse bias, junction J1 will be reverse bias, okay. Similarly, junction J2, okay, just observe, negative voltage to the N region, positive voltage to the P region, so this will be forward biased, whereas junction J3 will again be reverse biased. So this is exactly the opposite which happens in the case of when it is forward voltage VF, okay. So now the point is, there are two junctions which are trying to oppose the flow of current, and there is one junction J2 which is trying to help the majority carrier current flow. So the overall result is that I'll be getting a very lesser amount of current, okay, till a certain stage, okay. So this particular stage is called as reverse blocking region. Reverse blocking region, because again here also there is absolutely no current, right? Whatever current is there, it is mainly due to the flow of the minority carriers. So this is called reverse blocking region. Okay, fine. So what happens after that stage if I further increase VR? Okay, so if I further increase VR, the same avalanche breakdown happens, okay, so that there will be a sudden surge in the reverse current, okay. So this is similar to that of a normal diode, similar to diode characteristics, okay. However, in the first quadrant the characteristics are completely different, okay. So these are exclusively SCR characteristics, okay. So again, just to summarize, there are 2 to 3 important points. The first point is the forward blocking region, wherein there is absolutely no current. Okay, please understand, here the SCR is off. Okay, so what about this stage? This stage is the sudden reduction in the overall voltage, because the junction J2 gets highly reverse biased, and it is after that, due to the breakdown, that there is a sudden surge in the forward conduction current. So it is in this stage that the SCR is on. Okay, and which is the terminal that is trying to control it? Gate is the terminal that is trying to control it. Okay, so as the gate current increases, we will obtain the switching on action of an SCR at a lesser and lesser forward voltage. Okay, fine. So this was a slightly involved, slightly complicated procedure. All right. Okay. Next, so that's the diagram which is given in your textbook. Okay, a 4-layered structure being broken up into 2 transistor equivalents. So the first one is PNP and the second one is NPN. Okay, so you can very clearly observe that the gate terminal is at the P region here. Okay, so converting the structure into its equivalent circuit, this is how the equivalent circuit of a SCR looks like. So that's the first PNP transistor Q1 and the second one is a NPN transistor Q2. Okay, so just observe, the base of the PNP transistor is connected connected to the collector of the Q2 transistor. Okay, whereas the base of NPN transistor is connected to the collector of the Q1 transistor. So it's a cyclical operation. So what happens to the current? Let us just observe. Okay, so just focus here. It is during this particular stage that when Vg is 0, Ig will be 0. Okay, so Ig is actually 0, and in that case, so we are talking of this stage, okay, 0 to T1, right? So in this stage the SCR will be off. Okay, because just focus here. When Vg is 0, there is absolutely no current here. So when there is no current, right, what happens? IB2 is 0. If IB2 is 0, then IB1 will also be 0 altogether. Then what happens during this particular pulse? Okay, so during this particular pulse, the SCR will be on. Okay, just observe, from T1 to T2, okay, when Vg is being applied, Ig flows, and when Ig flows, the transistor will be on. Okay, since NPN is on, simultaneously PNP will also be on. See, the previous explanation that I did was with respect to the device physics, what is actually happening inside the device. Okay, this explanation is circuit wise. Right, now both the transistors are on, so a continuous current keeps on flowing now. Okay, now even if I detach this Vg, even if I make Ig equal to 0, still a continuous current keeps on flowing through the SCR, because we call it as the triggering of SCR. Okay, the SCR has got fired, triggering of SCR. Okay, now it cannot be automatically switched off. If it has to be switched off, then I'll have to detach this V. Okay, so that is called anode current interruption. Anode current interruption, or I'll have to apply a negative pulse. Okay, just I had mentioned, right? So if I apply a negative pulse, then also I can switch off the SCR. Okay, but generally this is called as on state of the SCR. Okay, the previous one was off state of the SCR, now it is on state of SCR. So the same thing is being explained here. How long is the turn off time and how is turn off accomplished? An SCR cannot be turned off by simply removing the gate signal. very important point once it is switched on. And it can be switched off only in a special few cases, that is by turning off the VF itself or by applying a negative pulse to the gate terminal. So there are two methods. The first one is anode current interruption and the second one is forced commutation. Okay, so that's the anode current interruption. Okay, so that's the first method. Either it could be in series or it can be in parallel. Okay, both the methods can be used. And the second one is forced commutation method. Okay, so you can just go through these things, and this is the same diagram that I had explained earlier. Okay, so just focus on it once again. So this is when the SCR is on. I can say that there is forward conduction current happening. Okay, so this is the stage when the SCR is actually off. Okay, and you will very clearly observe that when Ig equal to 0, okay, although Ig is 0, still forward conduction current can be achieved, but at the cost of a very high breakover voltage. So if you want to reduce this breakover voltage, then you will have to apply Ig1. Okay, which means you will have to control the operation of an SCR by using a third terminal at the gate. Okay, so that you will be getting this kind of a characteristics. If you further increase, then you will get the almost the same characteristics like this, right? So that is the importance of the holding current here. Okay, the latching current should have been mentioned, however, okay, see, this is called as IL, latching current. Okay, because it is beyond this stage wherein I can clearly say that the SCR has got switched on. Okay, fine. Now in the reverse bias, it is similar characteristics as that of a normal diode. Okay, fine. So you can just go through these points. I have explained them. What about the SCR applications? SCR finds its applications in many areas. One is as a static switch. You can clearly control its phase. It can be used in a battery charger, a temperature controller, single source emergency lighting system. Okay, so that's one application, series static switch. Okay, wherein it is used for rectification control. Now there may be a question in some of the students' minds that, sir, when a simple diode can be used as a rectifier, okay, what do you mean by rectifier? Conversion from AC to DC. Then why should we go for a SCR? Right? The first point is an SCR is used as a high power device, and the second point is an SCR is used as a controlled rectifier. Now what do we control here? We control the switching action. Okay, and the switching action is controlled in such a way that you can also control the phase of rectification, which is very important. Okay, so this is possible only in the case of silicon controlled rectifier. Okay, again it can be used as a variable resistance phase control. So here we have that word phase control, right? Okay, so just observe the output waveform, right? See, this is a waveform of a half wave rectification, right? But even in half wave rectified output, you can control the phase also. Okay, for example, you can just clip away this part. You can ensure that the diode conducts for only 90 degrees, not the entire 180 degrees. Okay, so such wonderful control is made possible only by using a SCR. Okay, all right. So I think we have discussed the basic symbol construction and the working principle, the characteristics, and one or two applications of SCRs. Okay, so in the next class we will be focusing on the variants of SCR which are called as diac and triac, okay, which are also equally important. Okay, so I think we'll stop here. Students, if you have any doubts, then you can ask me.